All right, what is up, everyone? Welcome to week 63 of Chill Kernel Hacking for Fun. Thanks for joining. I'm starting a little bit late today, so I still need to send out the tweet. So just give me a second while I do that. But yeah, welcome to another week. Today we are going to be continuing with networking. What did we do last week? So today we're going to start working on, I believe, the receive side of transmission. Let's open the Lab 6 docs. So we've done all of this stuff. And yeah, we did exercise 8 last time. So this time we are moving up in the world, and we're getting into part B, which is receiving packets and the web server. So yeah, hopefully that should be pretty good. So let me finish writing this tweet. Okay, so networking. Side. The networking labs this week will start on the receive side. What's the link? Also, test 0 in the chat. Week 63, yeah, been doing this for a minute. All right, tweet is written and published. Publish now. Just gonna double check that went out correctly. Week 63. Okay. Welcome to everyone joining. Hope you're having a nice Sunday. I'm also going to get my Twitch stream manager open in case anyone joins on the Twitch side, but things are kind of quiet on Twitch, so I don't exactly expect too many people to be there. All right, so let's get going. So I need a minute to, let's see where we are. So we had worked on the transmission lab last time, and we implemented this output helper service, which is a user space process that all it does is it receives data from the network stack, which is running in a different user space process, and it actually transmits them by just forwarding them to this system call. And I just have some random comments here that I think are not really that important. I'm just carrying this random stuff around. I'm just going to amend this into previous commit. All right. Test. I'm gonna do a test Twitch message. So yeah, this week we are getting started with part B, and so I'm hoping this won't be too difficult. This is going to involve getting back into the nitty-gritty details of the device driver for the NIC. And in the same way that we set it up to do transmission, we'll need to do a very similar set of steps for receiving stuff. I'm going to get out my trusty manual, which probably will be useful for this. Anything else I'm missing? Yeah, all right, cool. Okay, let's just read this for a second. Just like you did for transmitting, you'll configure this to receive packets and provide a receive descriptor queue and receive descriptors. Section 2.3 describes how packet reception works, including the receive queue structure and receive descriptors, and the initialization process is detailed. All right. What is it? It's April 13th, week 63. Exercise, read section 3.2. You can ignore anything about interrupts and check some offloading. You don't have to be concerned with the details of thresholds or how the card's internal caches work. Okay. The receive queue is very similar to the transmit queue, except it consists of empty packet buffers waiting to be filled with incoming packets. Hence, when the network is idle, the transmit queue is empty because all packets have been sent, but the receive queue is full of empty buffers waiting to be received. When the E1000 receives a packet, it first checks if it matches any of the configured filters, see if the packet is addressed to this MAC, and ignores the packet if it doesn't match a filter. Otherwise, the E1000 tries to retrieve the next descriptor from the head of the receive queue. If the head caught up with the tail, so from the head, so the hardware is always taking things from the head of any queue, basically, whether it's the transmit queue or whether it is the receive queue. In the transmit case, the hardware is looking at the head to see if there is a descriptor that has some data waiting to be sent out. And on the other hand, on the receive queue, the hardware is looking at the head to see if there is a eligible slot with a descriptor that is ready to get some data put into it. Nice. Welcome to everyone joining the stream. All right. Yeah. If the head has caught up with the tail, then the receive queue is out of free descriptors, so the card drops the packet. If there is a free receive descriptor, it copies the data into the buffer, sets the DD bit and a packet, and packet stats bit, and increments the RDH, the head. Right. Again, I'm going to find it super useful to have one of these diagrams. I'm going to find the equivalent diagram, but basically, I mean, for the moment, I'll just copy this. So we have this queue of stuff, and when we initialize the queue, we initialize it completely full of descriptors. And so the head is going to point, let's just say it points here, and the tail, they're both going to start out at 0, but when we initialize the receive descriptor ring, we are just going to loop through every slot, initialize the descriptor, and point it at a memory buffer. And the tail is going to literally move all the way to the end, I think. Or possibly here. I think actually we still, for the transmit side, we reserved one free one. No, or maybe yes. Wait a second. Maybe we should pull it up. Yeah, we reserved one free. So We get the tail, we get the next, and if the next one does not have the DD bit set, then the buffer is full. So that would mean, so just to review, so that means, so basically we initialize them all at the start actually. A DD bit for the transit queue means it is processed and free to be used. And so basically we initialize all of them to have the DD bit set. And then and then gradually we push the tail and we clear the DD bits. And then let's just say we cleared. And so we're here. DD bit should be set on both of them. But let's say we're, let's say we're here. Let's say we're here. We assert that the DD bit is set, meaning we're empty here. And then we check the next one to see if it's not set. Not set meaning it's not free. And so this one has the DD bit set. So they're all set. So it's still set. So it's still set, and so we continue. But let's say we get here, and let's say the hardware still has not processed this head. Then we're going to check the next one and see that it is not set because we cleared it when we populated it. So this is going to be not set, and so this is the full state, and which means we leave this one empty. And I think it will be maybe a similar situation for the receive side. The E1000 receives a packet that is larger than the packet buffer in one receive descriptor. It will retrieve as many descriptors as necessary from the receive queue to store the entire contents of the packet. All right, quick 20-second break to stand up and stretch. Be right back. Right, so if we receive a packet that is larger than the buffer in one descriptor, it will receive as many descriptors as necessary from the queue to store the contents of the packet. To indicate this has happened, it will set the DD bit on all of these descriptors, but only set the EOP bit on the last of the descriptors. You can either deal with this possibility in your driver or simply configure the card to not accept long packets and make sure your receive buffers are large enough. And that's like the way I'm going about this right now. So I'm just gonna copy this in. So we need to make sure to remember to do disable jumbo frames to start. Okay, let's quickly check out section 3.2. Packet reception. Hardware stores incoming packets in host memory subject to the following filter modes. There's insufficient space, hardware drops them and indicates the missed packet in the statistics registers. Following filter modes are supported. Exact unicast. Destination address must match exact Windows 16. Stored. Receive all unicasts. Multicast the upper. Oh, Twitch message. What's up? Volvo Tech, is it possible to compile C program with GCP to target no platform that is directly read by bare metal? Yeah, pretty sure. Yeah, that's what I'm doing. C programs, and you just pass some special flags, and you don't get any libc or anything. Yep. My boy Offna, what is up? Thank you for the test one. Appreciate that. Hope you're doing well on this fine weekend. All right. Promiscuous unicast, receive all unicasts. Honestly, I kind of don't know what these mean. It's been a long time since I've thought of networking, and I'm not exactly a networking expert, and so I don't have it locked in exactly what unicast or multicast mean. I know it's something along the lines of on a hardware level, I don't know, sending out packet to anyone on the network or something like that. Honestly, I don't really know. Multicast, the upper bits of the destination address index a bit vector that indicate whether to accept the packet. If the bit in the vector is 1, okay. Apparently you can have some more fine-grained control about whether you want to accept something or not. Promiscuous multicast VLAN, receive all VLAN packets that are for the station. Okay, this is kind of complicated. I'm not sure. I just want the simplest of these, whichever, and I'm not totally sure which that is. It might just be the exact one, or maybe just promiscuous. Maybe I'll just ask ChatGPT what's the difference between unicast and multicast. What's the difference between unicast and multicast in networking? One-to-one communication. Single sender sends data to a single receiver. Right. So unicast, simple one-to-one. Multicast, one-to-many. Transmits data to a multicast group. Only devices that join the group receive it. Okay. That's useful. What I think the simplest thing for me is I just want to receive anything from anybody, and I don't exactly. I think promiscuous unicast might be what we want. Or ideally both, maybe. Promiscuous multicast and promiscuous unicast. Normally only good packets are received. These are fine. CRC, no errors, blah, 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 blah. Alternatively, you can, if the store bad packet bit, then bad packets are that pass the filter functions are stored in memory. Packet errors, it's possible to receive all packets regardless of whether they are bad by setting the promiscuous enables and store bad packet bit. Okay. Nice, we got 18 people in the stream. Thanks for joining. How do you run it though? Or maybe yeah, that's what I do. So yeah, I mean, actually running that program is a little bit more complicated. You need to make sure, like, it's basically integrating it into the boot process. But yeah, I mean, I use Kimu, yeah. I think I'm not seeing all the chat messages actually. Catflare and Donna Skis, yo. What is up, Catflare? What's up, Donna Skis? Okay. Let's keep reading this. Okay, so we know, so basically receiving is a little bit more complicated than transmitting, apparently. There are some filtering modes we need to be aware of. Memory buffers pointed to by descriptors. Hardware supports 7. Yo, what's up, Ismail? Nice to see you again. Hope Bacon's good today. Me too. Chillin', that's exactly right. Okay. Okay, so there are some requirements about the buffer sizes that, okay, we can support. I think we've been using 2048 bytes for the transmit queue, and I think we'll just stick with that. Donoski's, this is a PC. Yes. So I actually don't know what 802.3 means, but yeah, it's a wired Ethernet network interface. Yeah, it's the Intel E1000, which is apparently one of the most popular or a very common NIC. So probably want promiscuous mode for unicast and multicast. I see, okay. Probably there are fixed sizes. Thank you. Yeah, okay, 802.11 is for Wi-Fi, yeah, right. Yeah, I mean, and just to be clear, it's kind of a hobby OS, but it's also sort of not, because I'm just following this like lab coursework for this OS course, and so they wrote a lot of the OS. But at this point, I've also done a lot of work on the OS. But yeah, I think a lot of hobby OSs don't have networking. Maybe, I don't know. I haven't read that many or used that many hobby OSs, but I think it's a little bit less commonly worked on, and I can kind of see why this stuff is like kind of annoying. Okay, there's a lot, like this manual is so big, it's really huge, and it would be pretty difficult to write a driver for this kind of thing without a lot of experience. I think I'm trying not to copy code from other OSs, but I'm even failing that at some points. This manual is incredibly large, and like we're like it's like 500. It's a 500-page manual, and we are using like 1% of the functionality of this NIC right now. There are so many features that we're not using. What's up, Sita is 22. So this thing that we're looking at right now is the manual. Why can't I scroll up fast enough? Okay. It's like the manual for this family of NICs. E1000 manual is how it's like what I've called the PDF. Yeah. Okay. It do be crazy. That is exactly right. It do be crazy. I'm just gonna give a quick test of my audio effects also. Some taps.
Haters gonna hate. Haters gonna hate.
All right. Yeah, so, okay. Receive descriptor format. So I think this should be pretty similar to the transmit descriptors. It is. Yeah. Honestly, I'm not even sure we need to care that much about it. there's some descriptors. Okay, and we have, so each descriptor, so basically, so just take a step back, we have these rings, and receive descriptor queue, here we go. Here's our receive queue. Hardware maintains a circular ring of descriptors and writes back used descriptors just prior to advancing the head pointer. Software adds received descriptors by writing the tail pointer with an index of the entry beyond the last valid descriptor. Yep. As packets arrive, they are stored in memory and the head pointer is incremented by hardware. Right. So bring to the front. Or rather, maybe it's better to just illustrate this with some stickies. So let's say we have a descriptor ring. It looks like this. I feel like I'm super slow at understanding this kind of stuff, but okay. So on initialization, what we actually need to do is mark all of these as available, which means we populate the descriptors. So we loop over and yeah, and we're gonna initialize all of these, and each of these needs to point at a buffer. Okay. Although I actually, except for this last one, I think the way I've been doing this is to basically not use the last one, because if I use the last one and I actually populated it with an empty, if this was like the completely full descriptor, then I would need to push the tail all the way back here. And then I believe this queue looks like it's empty because the tail is equal to the head. So I think that's not allowed. And so I think I actually need to keep this free. That's what I've been operating under the assumption of. What's up, Digitalized? Good to see you, dude. Where are you at the end of the development of this? Have you implemented the Mac layer, for example? So one very important part of this is that for all of this work, we're not writing a full network stack. We are using LWIP, which is an open source network stack, and that's, as far as I understand, that is implementing actually like Ethernet and stuff like this. Well, what I'm doing in this lab is writing the driver and a bit of the glue that will basically port LWIP to our platform. And so LWIP needs, basically it produces packets to be sent out, and then it just you need to implement a function that does something with those, and that's what I've been doing. And so, yeah, we're not implementing an entire network stack. Yeah, it'll take years. I'm definitely not that good and not good enough to do this. So, yeah, if I were to really do an OS, I don't really know if I'll go all the way to do all that stuff. That sounds not that fun, to be honest. All right, so So we were kind of just getting a firm understanding of how this queue thing works. So my understanding is that, okay, let's call these things populated and full, and this one is actually not. And so this is how we initialize the buffer, and then what's going to happen? What's going to happen is that we're going to receive a packet, and these are each going to be 248 bytes, which is big enough to store the largest possible Ethernet frame. So we don't need to worry about it consuming multiple stuff. So basically each of these descriptors and these buffers corresponds to one Ethernet frame, nice and simple. And what's going to happen is the hardware is going to consume one of these buffers, writes the data into the buffer, and then it's going to, I believe it's going to advance the head. My huge question mark, how does the OS know to add more buffers to the receive queue? So basically, with the transmit side, it was a bit easier because every time we just wanted to send a packet, we would just push an entry onto this queue and increment the tail. But on this side, the hardware is just like pushing stuff into this queue. You know, potentially it looks like this now. And I think, and then it looks like this, because let's say the OS didn't do anything. The hardware just consumed all of the space, and from this point on, it's dropping packets because the queue is empty. And I'm not really sure how the OS because the OS needs to it needs to know that, okay, we need to push some more like packets here. And I suppose that is going to happen when we process the data. So if we just back it up a little bit, let's say it looks like this. So this, so these things mark like available buffers, and these are used. Was that already 20 minutes? Crazy. All right, 20-second break. Be right back. Make sure to stand up and stretch. Right, so this one has been occupied and hasn't been. So now, let's just say maybe the OS is like spinning and pulling this. It's going to see, how is it going to know? What is it going to do? I guess I believe there was some race condition about the head pointer, and so it's going to, right, so how does OS know there's data? So I believe it will set the DD status bit on all these descriptors. So then this thing gets a DD, right? And we need to somehow scan for these. We need to look for with DD bit set. interrupts, we're not caring about receive interrupts or potentially checksums. Okay, maybe let's go back and read this in a bit more detail. Maybe they explicitly say how we should do this. So descriptors are a data structure pointing to a buffer and have some fields. And some fields are modified by hardware upon packet reception. Status length. For standard packets, blah, blah, blah. I don't really care about the checksums. So I may modify the starting offset. Okay, that doesn't matter. Status. So, okay, maybe I'll just take a screenshot of this. It'll probably be useful. So we have this thing, and maybe I'll just put this very close to here. So this thing, it's like sort of like these things, basically. And we have some bits. And that corresponds to okay, cannot exactly point, but it's like approximately to this field. No, well, to the, yeah, can I crop this? Custom. Okay, points to this field. And I don't know how important this stuff is. Reserved. Really, the only things we care about are end of packet and DD. I think we can kind of ignore all the rest of this stuff. There are some error fields. Which are only valid when these bits are set. Okay. I'm going to ignore that for the moment. Special field, I also don't really care. Okay, receive descriptor fetching. The descriptor fetching strategy is designed to support large bursts across the PCI bus. This is made possible by using 64 on-chip receive descriptors and an optimized fetching algorithm. This fetching cache line or descriptors each. So what does this mean? Receive descriptor fetching. This means that the hardware needs to read this array out of memory of descriptors. It's not doing this one by one. It's reading in large chunks, and it stores 64 descriptors on the hardware side. And I don't really know what PCI bandwidth means, but it fetches a cache line or more with each burst, and the cache line, I don't know, 64 bytes. And so these are 16 byte descriptors. So we get 4 descriptors per burst. Do I need to care about this though? When the on-chip buffer fetch happens as soon as any descriptors are made available. When we write to the tail pointer, it fetches. There's this pre-fetching. Okay. Wow. The bit offsets still bother me in the diagram. That is so true. Why is this 32 all like slightly to the right? It should be, or is it? No, it's like it has to be a bit to the right. It's not completely aligned. Yeah, I'm with you. I don't know if we need to care about this though. Okay. Receive descriptor write back. Processors have cache line sizes that are larger than writing back descriptor information. What? Okay, so it's talking about write back now. And this is relevant when the hardware is writing to memory, and it's literally writing to memory into these bits, and something to do with that. Partial cache line updates. Right, so it's saying the hardware needs to set bits in these descriptors when it puts data in memory. Okay, number one. But number two, these descriptors are almost always smaller than a cache line. And so, yeah, if we were to just write the descriptor for each packet, you need to update the entire cache line, actually, and that's expensive. So apparently there's some ways this is made efficient. Again, it's like one of the hard parts of reading these manuals is actually figuring out what is the important information and what is irrelevant, at least for now. Packed together and written as a cache line whenever possible. So for example, if for, so in our case, for descriptors is a cache line. Maybe let's just make this a little bit bigger. 1, 2, 3. Okay. Let's say our ring buffer has 8 descriptors in it, and so and since each of these is 16 bytes, it covers 2 cache lines. And let's say the hardware had 4 packets come in really fast. Instead of doing it one by one and writing each descriptor into memory individually, I believe what this is trying to say is that if it's possible to have 4 of them, it will try to do all of this in a single write to the cache line, to do a single cache line write, basically. And apparently you can even control this. There's some thresholds or some timers. Wow, that's crazy. Okay. Again, I don't think I need to care about this, so I'm going to keep going. Hardware stores no data in descriptors with a null data address. Software can make use of this property to cause the first condition. I didn't totally understand that. Make use of this property to cause the first condition under received descriptor packing. Oh wait, first description. Which is some number of a threshold is reached of. And I think it's talking about internal descriptors. Okay. And apparently you can write some null descriptors with the DD bit set. Okay, I don't know. Okay, the descriptor ring. This sounds important. Hardware maintains a circular ring and writes back used descriptors just prior to advancing the head pointer. So basically, right, that's what we kind of talked about before. So originally, this was all like empty. The hardware came in and populated some bits in the descriptor, right, just prior to advancing the head pointer. So it does that, and then it bumps the head pointer. Software adds received, right? By writing the tail pointer with the index beyond, we already saw this, they are stored in memory and the head pointer is incremented. However, when the hard pointer is equal to the tail pointer, the ring is empty. So that, right, we were kind of talking about that earlier. It's very important to make sure that when you do all this like initial population to fill up the buffer, you do not completely max out the buffer. Otherwise, you would push the tail completely back to the head and the whole thing would look empty. And so I think for that reason, it's actually important to never to fill every single slot and to always leave one slot empty. That is my understanding. Hardware stops until software advances the tail pointer, making more received buffers available. So I don't know how this is going to work in the OS. The lab notes will hopefully maybe give us a bit of guidance. My assumption is that we're going to have some kind of process or task or something that is going to pull here, and it's going to be constantly checking something. It's probably going to be checking if the buffer is empty or not, or no, if the buffer is full. If the buffer is full, meaning full of empty packets, there's nothing to do. But as soon as the buffer is not full, meaning that there is data that is pushed in, we're going to do something with that data and then refill the buffer. We're going to do whatever it takes to process that data, which might mean copying it out into some other buffer where further processing can happen. But we're always going to try to keep this buffer this ring as full as possible in order to prevent the situation where hardware just bumps and fills the whole thing up, and then we're just like sitting there unaware of this and we're dropping every single packet that comes in. So this is my guess, and we'll see if this guess is right. The more advanced way to do this might be to actually use interrupts, because I think you can get an interrupt if a new packet comes in. But so far, it seems like we're doing things very simply in the OS. We're just going to do a polling, some kind of like polling task, and that might even be what this input helper environment does. We're going to have some kind of driver function that receives or receives. The input helper, I think, is likely going to be just in a loop, like calling this receive and forwarding data on. So that's my guess, and we will see if I'm correct. Okay. So this is a very familiar diagram. Shaded boxes that have stored incoming packets that have not yet been recognized by software. Right, meaning, okay, so all of these are empty slots and hardware had filled up all the shaded areas with data. And so what software needs to do is it needs to, starting from the tail, process every single thing and kind of bump all the way along until it reaches basically close to the head. Again, not completely filling up this last slot, but it needs to, So the algorithm is something like, okay, it's time to do some receiving. Tail is it points at a free slot, basically. No, not a free, a filled slot. We just go along, bump, process, and we're going to stop here. So we're going to be here. We're going to process this data. We're going to mark it as available, and then we're going to stop here. Otherwise, we would bump forward one more. So we just like leave. We process. Wait. But this means there was some data actually put in here. So it's actually a little bit unclear to me what happens in this case. Because if we process the data, we can process the data, but maybe we just don't mark it as free yet, because otherwise we need to push the tail. I do not have an abstract data type over. I don't have any data structures or anything right now. I think if we were doing production code, we would definitely do some refactoring to abstract over this. But for the moment, I'm just really just like raw coding it at the moment. Yeah. It's literally just like C arrays of structures. Yeah. Okay, so anyway, so that's not super new. So here, I think here is like super important. You can tell that it's super important because this capital bold thing. The head pointer points to the next descriptor that is written back. After the completion, this pointer is incremented by the number of descriptors. Hardware owns all descriptors between head and tail. Just to be clear on what that means. If there are descriptors in this region, do not write to them. do not even read them potentially. You're only allowed to read things that are outside this region. And when the hardware puts some data in here, it increments the head pointer to let you know that it's now under your control. Okay. So we have some registers. This is not really news. This is exactly the same as how the transmit queue worked, I believe. If software statically allocates buffers and uses memory reads to check for completed descriptors, it simply has to allocate the 0 status byte. Okay, 20 seconds, be right back. So, if software statically allocates buffers and uses memory read to check for completed descriptors, it simply has to 0 the status byte to make it ready for reuse. This applies to us, I think. So what is this saying? So we will be statically allocating the ring buffer, and to check for completed descriptors, we're just gonna be checking each of these to see if the DD bit is set. And it's just saying your scan will not work if you don't reset the status byte. So, okay. So this is the part we don't need to care about, I think. Receive interrupts. Okay, I think that is enough reading. I think we can actually begin coding now. Set up the receive queue and configure the E1000 by following the process in 14.4. Wait, what was 14.4 again? Dang. Receive initialization. Okay. Okay, so this is a sort of a step-by-step guide, possibly. That's what we need to do. And I learned my lesson from last time, actually. I think last time with the transmit queue, we spent a lot of time initializing stuff that actually was not implemented by Kimu in the first place. And that was very time consuming. It was kind of a waste of time. So I think I'm going to try to be a bit more aware of this time and maybe even skip exotic things that are not needed. So let's read this. Program. So this is immediately one difference. Program some registers with the desired Ethernet address of whatever we want our Ethernet address to be. Should always be used to store the individual Ethernet MAC. This can come from the EEPROM. Okay, I don't really know. So I guess we need to choose an Ethernet address or something like this. Initialize some table rate to 0. See, there's no immediate reason to enable the transmit interrupts. I don't want any interrupts, I think. I don't want any timer delays. Okay, allocate memory for the descriptors. Align it on a 16-byte boundary. Okay, we need to do this. Just make a note. We need to do this part. Receive buffers should be allocated to endpoint. Software initializes with the head and tail. This is a bit confusing because the transmit queue, I think the head and tail used indices and not addresses. Does the coursework say anything about this? Be careful with the byte order. MAC addresses are written from lowest. You should use at least 128 receive descriptors. Holy crap. That is significantly more than the transmit queue, actually, because, and wow, how much memory is that? 128 times 248, right? 256 kilobytes of receive buffer space is what we're going to use. So that's kind of a lot of memory, but okay. Okay, then there's like more stuff here, but so far we're just trying to initialize the receive part. What's up, Samarth? I'm good, man. Can you please make a roadmap for us to learn everything? So I don't know everything. What I can do for you is link you to this course and link you to the resources I have gathered, which are not really like that great, but might give you a bit of a start. Okay. Configure the E1000 to strip the CRC. So I'm just going to make a bit of a checklist for myself of things I need to do. Hey Zara, nice to see you again. Hope you're doing well. So checklist would be, we need to don't allow jumbo frames, strip the Ethernet CRC, set the Ethernet MAC address, alloc the ring, the RX ring, alloc the backing buffers for RX ring, initialize the RX ring to be filled with empty buffers. This is a basic list of things we need to do. And yeah, these are a bit easier. I don't really know how to do this stuff. Yeah. Okay. Anything else relevant? And then there's a bunch of these control registers. Okay, so the enable bit, it is best to leave the receive logic disabled until after the ring has been initialized. Okay, so set the control register. Enable bit set at the end. Oh, okay. Long packet enable, that's easy. So that's just part of this control thing. Minimum size. That's not, I don't really know what these things are. Okay, so this is also the strip bit. If it is desired for hardware to strip the CRC prior to DMAing the received packet to host memory, okay? So apparently all this stuff happens in the control register. Okay. Okay, I'm going to clumsily get started on this. Thank you for just watching me read manuals forever. I'm going to get rid of all these old tabs. Clean editor e1000.c. Our Git is like a little bit dirty. I'm just maybe I'll just amend this one into here. No, this was for the syscall, right? I'm just going to amend this into here. And this is just some init stuff. I will actually bring back this panic. I actually want to panic again, I think. So I'll bring back the panic. Do we compile? We compile. All right, let's get started. So, what's up, Publish? One day I'll work on a PCI driver. Love to see it. Thank you, Publish. One day, yeah. I mean, yeah. I mean, it's difficult, but I'm doing this extremely clumsily right now. I think I just want to show that it's not that magical to write a really bad driver for these things. Like my driver is super bad. Okay, so here's what we need to do. So we have our init function, and so far we were initializing everything directly here. What if I could make a function, but maybe I just won't. Maybe I will just do this everything in line. Initialize, receive. clear out some space. Okay, we need a couple of obvious things. So, a few obvious. So, I'm gonna make some copies of all these defines. We need. It said we needed 128 RX descriptors. Each of these will be 248, and the total RX backing buffer size will be K RX descriptors times, and we need K RX backing buffer size. We'll call this K. Does this work? That did not seem to work. Okay, we'll call this K. Don't take the K naming too seriously. Like, I'm just like sort of a bit used to that naming scheme, but you're also not really supposed to use, like for macros, you generally use all caps. I just kind of hate all caps. So I'm just not using them. Okay, so we have some basic constants declared for our receive side. We have 128 receive descriptors, 2048 bytes for each backing buffer, and define for the total size of all of the received backing buffer, which is just these two things multiplied. So now we can go into here and we can allocate the memory in the same way. RX backing buffer, very simple, nothing magical going on here. RX descriptors. So now we need to declare a structure for the RX descriptors, and at least I have this example of how to do it from the TX, which is kind of nice. Let's declare our structure based on that. To do that, we need to go look at this thing, which is the descriptor layout. So we have an 8-byte buffer address, which is right. We have a 2 16-bit buffer length, that's also the same. We have a 16-bit packet checksum. I'm just going to call this packet checksum. And also, wait, this is also 16 bits. We have an 8-bit status. We have an 8-bit error. Wait, the status is actually 8 bits. We don't need the bit field. We have an 8-bit errors. Error. We have another 8 bits. No. 64 minus 48 is 16. We have 16 bits of special. So that's what our receive descriptor looks like. And so now we can go ahead and use that right here. So now I've allocated the backing buffer for all the receive descriptors and also the receive descriptor ring, which are on these two lines. And I'll just give myself a nice little git commit to get started, I think. I'll do this in fork. So let's stage this, stage this, stage this. Actually, we don't need this new line. Stage this. This will come later, but just quickly kind of locking in a little bit of stuff I know we will need. Okay. Moving on. So let's go back to this huge list of things to do. So maybe I will start with some of the easier things. So we need to do this, right? So we need to program a base address register. So let's do that. This is also pretty easy because it's exactly the same as for the transmit side, basically. And so what we need to do is except it's, okay, so we need what register? RDBAL. It's RD, we're just basically changing a bunch of T's to R's everywhere. And hoping that I don't forget anything. So we set this thing, RD_len, right, the bytes of the descriptor ring, and okay, so basic, this is going to be a bit of a to-do. Is this correct? Are the head tail indexes also for receive? That was a bit of a detail I wasn't sure about. Well, technically we should actually we should actually fill the ring buffer with empty descriptors. Okay. Now we're getting into some of the hard stuff. So I already know we need to set the control register here, right? Oops. Control. Okay. You have to configure the receive address registers with the card's own MAC address in order to accept packets addressed to that card. You can simply hardcode Kimu's default MAC address. Okay. So we'll do that after we all stand up for 20 seconds. Fair back. That will come later. Let's focus on this Ethernet MAC thing right now. It says, program the receive address registers L and H with the desired Ethernet address. L and H should always be used to store the, also, wait, I'm just remembering, I was just kind of blindly using these macros. But yeah, these are declared in this header file that we stole from Kimu, which I hope works. We did a limited amount of declaring our own constants. Did we? No, not really. Apparently not. Okay, this whole head like constants thing is always quite painful. I'm actually doing these 20-second breaks now. Nice. Okay. So we need to program some registers. It was telling us, so here is the MAC. Be careful with the byte order. MAC addresses are written from lowest order byte to highest order byte. So blah, 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 are the lowest order 32 bits. Okay, I am kind of confused about this byte ordering thing, actually. Yeah. So we have a MAC address here, and we need to write it into the register, but well, yeah, and it's explaining to us MAC addresses are written from lowest order byte. So basically, yeah. So first off, these 4 bytes are going to be in the low register. But what exactly is the order? It might need these. It might. I think this actually needs to be flipped around such that the 52 is like it's really on the lowest side. I don't know. Let's just try it. So we need to write some registers. We need to write it's RAL and RAH, which doesn't have a define. So receive address. How? I'm really bad at this ending and stuff. Yeah. Okay, so I'm looking. So this is a giant file, and I'm looking for a particular register, and I'm not really finding it. So I guess the thing to do is to really go to the manual and look at the register descriptions and look at the main register descriptions and look at search for RAL here. Or maybe if I go over here, actually back to, or was it 14? Maybe they will link. Or maybe I can search for this text. Receive address register. I search for RAL. Why did it give some? I do. Receive address high. I'm going to highlight this. Okay. Receive address low. 16 register. So the interesting thing. Oh wait. So yeah, you can program in multiple Ethernet addresses into this thing. 16 registers contain the lower bits. All 32 bits are valid software. Okay, so it seems, so this is super relevant. And what I'm looking for is this number 5400, because I want to find that in my constants, or E1000. Or maybe it's in this one, 1000x. There we go. It's this RA thing. Receive address read write array. Okay, so we need this thing. Are we including that file? So this thing includes this X thing too, so we should have it. So, okay, time to write in the lower 32 bits. And I'm just going to do that. Oops. Right here. So, and it's just going to be a number, right? And that number is what? It's 12 00 54 52. 12 00 54 52. I'm just going to copy in this entire comment. Okay, and then something, wait, RA receive. Address. Receive address. What? 5404. Oh, interesting. So these things are like, so this is a 32-bit register. And this one is right next to it, going higher. So it's actually an array of 64-bit integers. I see, okay. Yo, what's cracking? So then here, so actually what we need to do is we write a 32-bit integer here, and then we do this plus 4, and we write, I don't know, we write some other number. 16 registers contain the upper bits of the 48-bit address. The complete address is. Okay, when writing to this register, always write low to high. When clearing this register, I'm going to assume it's talking about both of these collectively, maybe. So what we need to, so now we have some other thing here, and I'm going to guess so then we need 34, 6. That's a little bit of a guess. My reasoning behind this guess, it's saying, here's the address. It's saying this, it goes from low to high, and this is the low. So if we're writing into memory, the thing on the right side of this number is the low bits, and so it's like flipped around. And we basically just go from right to left and then keep doing that same thing all the way across the number. So that is my guess at how to do this stuff. So I'm gonna call that done. This is like this huge list of stuff to do. multicast table array. Can I so I wonder, is this right here? Okay. This looks very complicated. I think I'm just gonna skip that. I'm going to slightly cheat right now. I'm going to look at xv6 and see how it initializes the head and tail, because I think it means indexes here. With the transmit queue, it meant indexes. And yeah, I'm just gonna open recent xv6. So let's take a look at xv6. And here is where it initializes the receive, and it does some stuff, but here it's setting head and tail to indices, I think. So that looks right. Also, it actually is initializing the multicast table. I'm just going to copy this, I think. Okay. Oops. Should wait. Okay. So it's setting. So our version of this is my weird API called write32, and it's writing, I believe, in 32. It's just writing. So there's 4096 slots, but then there's this is the number of words, I guess. And zero. I'm just going to try this. So it is. So you can tell that xv6 is indexing into this 32, this array of 32-bit numbers by how it uses a +1 here. And interestingly, okay, also kind of low-key copying how it did the MAC address. I did this correctly, except it is setting the high bit for some reason. Did I miss something about that? Why do we need the high? Do we need the high bit? It's AV. What is AV? Does it explain what AV is? Address valid. Determines whether this address is compared against the incoming packet. When set, the address is valid. Interesting. Oh, okay, so apparently you need to do this to signal that you've written something here actually. Otherwise, it doesn't do any of this comparing stuff. So I will take a queue. So how would I have known to do this, I guess? Did it say anything about this in... Maybe it just assumes you went to the documentation for every register you write to and fully read this out. Okay, I'm going to quickly do this. So I'm going to do it in the same way, I think. Okay. Okay, setting up the MTA. Right. Okay, so we have ostensibly, so we technically shouldn't do this actually. We should legit fill in, I mean, we can set the head to 0. We should fill in everything. What's next? The control register comes at the end. That's like a ton of stuff. So I've done all this, done this, have not done this yet. This comes later. Okay, what's what to do? Let's fill in this thing. So this is going to, we're going to fill in all the stuff and then point to the very end. So it's actually just this constant, this k thing. It's like this k rx descriptors -1. Because the way we're going to initialize it is, it's illustrated here like so. It's gonna look like this. Everything gets initialized except for the last one. And tail is going to point here. Okay, and we're going to have what, a for loop, 0 less than k num -1. And it is time to stand up for 20 seconds. Be right back. All right, so in this loop, we need to go through every single descriptor and set the descriptor, point it at its backing buffer. To do this, we probably will need some structures. Maybe not, actually. Do we? Oh wait, yeah, obviously. So we just did this. So yeah. So we have our structure definition over here. And it's going to be an Rx. It just equals GRX descriptors I. Address of. Okay, and I don't know. Buff. I mean, do I even need this really? Just to keep it really broken down. So we have our things right here. It's the GRX. Descriptors. How did I do this? I'm just gonna look at how I did this. I computed against the buffer, right? It's the, yeah, that. Buffer backing size. TX. Okay. Zara, how much further along are you in the course and starting? I am almost done with the course. The course, I started from lab 1, which is all the way back here. And lab 6 is the final project, basically. Technically, there's a lab 7, which is if you choose to make your own final project, but lab 6 is the default final project, and that's what I'm doing. So I'm almost done with the course, at least for my kind of like initial pass through it, where I didn't do any of the challenge exercises or anything like that. What I find so rough about in this lab is, in particular, is I need to hand calculate that bit shifts are actually correct. Yeah. Okay, so the way I did this last time, I just kind of the interesting thing about how I'm doing this bit math is, it's because I'm using chars, so that means it's super easy. So here, I mean, I could also make a function, get args descriptor backing buff, exact same thing. Shit. So, you know, each of these things is going to be 20, 48, so just multiply it by that. So here, then yeah, get receive backing buffer I. We're going to need I'm just kind of spamming stuff a little bit sloppy. We have a forward declaration because we're going to need that here. And then desc p bucket phys adder equals p adder buff. So that's the first. And I guess also we should be clearing the status, right? I think those are the only things we need to do. What's a MSD crafter? We can see here that the majority of this stuff is not controlled by software. It's really just the buffer address. Hardware is writing to the vast majority of this. And we just got this slight guidance from the documentation to zero out the status byte to make it ready for reuse. So that's actually all we need to do, and maybe, yeah. Backing buff. So RX ring everything except the last. And so this means, yeah, we're looping over everything until this -1, so 0 to 126 and not 127. And so we're doing this, we're leaving this one empty, and then with this tail line, we make it point right here at the end at 127, which is one past the end of all the things we pushed in there. Any idea why they'd want to remove padding on those structs? I'm not sure what you mean. Remove padding. Yeah, what do you mean digitalized? It looks like this thing is like kind of remove padding. Sort of looks like everything is already kind of like packed to me. Although, were you talking about a different struct maybe? Thanks, Zara. Yeah. Yeah, it's been a journey for real. It's been over a year, but definitely learned a lot, and feeling a bit more ready to work on my own operating system at this point. The C code. Oh, with the attribute hint. Padding. Oh, you mean with the pack? Oh, I see. You mean this thing. Okay, sorry. I was like totally misreading it. So the reason with this, that's because we're making these structs, and we're making these structs to match a very specific memory layout that's in the manual. It's extremely important that we're writing to like very specific bits in memory. And so, yeah, for example, I mean, with the receive descriptor, it doesn't really matter that much because things are byte aligned. But if we go back and look at the transmit descriptor, this thing is different because we have these entries that are not byte aligned. They're bit aligned. Although actually maybe it matters in other cases, but basically the manual has this very specific specification of basically it's a struct layout, and we're writing a C structure that matches this, and it's very important that the C structure doesn't accidentally like include padding that will make our C struct mismatch with what the manual specifies. So that's why we explicitly don't have padding for these structures. Yeah. Okay, so we are making progress. Set the Ethernet address, set the MTA, cleared out the MTA for some reason, set the low and high address registers to the physical address of the descriptor ring, set the length of the descriptor ring, set the head and tail pointers, filled in the buffer initially, and I think we need to set the control register now. Myriad colors. As far as I know, malloc may pad your struct. Malloc. So first of all, we're not using malloc here, but yeah, with malloc, the padding that refers to is like when you ask for a certain amount of memory from malloc might actually, the buffer malloc gives you might actually be longer than what you needed or what you asked for padding reasons, but it's not going to insert padding spaces internally into like your structure or something like that. So we could also malloc these structures. The important point is that we use the packed attribute to make sure these things are guaranteed to match these struct layouts that are specified in the manual. Okay, let's see if I can quickly. I know this last part is always kind of crazy. Program the receive control register with a bunch of values. So the last time I did this, I used a structure also, and I might just do that again. That was kind of an easy way to do this. RX control register, and what does this register look like? Do I already have that screenshotted? No, I don't think so. So time to go into here, and I need to RX configuration word. No, that does not look right. Device status. Receive control register. This is all right. Transmit control register was here. That's this thing. Receive control register is here. Okay. What are you using for allocations? I am using static allocations, which just means global variables, just global C variables. I actually don't even have a memory allocator in the OS. The only memory allocator I have is a page allocator that just hands out 4K pages. I don't even have a malloc. Are those the specifications? Yes, this is the device specification. Oh, interesting. So this is like kind of cool actually. So I actually don't need a structure for this because it's literally bits, I think. It's like everything is bits. There's no numbers here actually. So that's actually really easy. So I'm going to just delete this whole thing. So the last thing we need to do is write at, hopefully I have something for that. And we're just going to write a bunch of stuff. And it's going to be a bunch of bit offsets. So maybe I will make some, I don't know, RX, some defines for, okay, even better. So I'm going to have the enable, right? And that's probably, that's bit 1, interesting. Okay, I'm going to have unicast promiscuous enable, which is bit 3. I'm going to have multicast promiscuous enable, which is bit 4. I don't really know what those mean, or maybe actually maybe I won't enable them at first. Long packet reception enable. So actually, I want to leave this at 0. Yeah, but I'll add this thing anyway. Loopback mode. So what were the things we wanted to suppress broadcast accept mode, receive buffer size. Okay, I think we, oh wait, what this is, ouch, okay. Maybe it's still okay. So, buffer size is 16 and 17. Key size. It's 17. So yeah, I'll call it 16. So what I want here is basically just a bunch of stuff. E1000 RX enable, board width. Yeah. And then basically what we're going to do is we're going to say software to trade off. Small buffers. Oh, this is interesting. B. Value. It's a 2-bit integer. We need to write in. Oh, it's default initialized. I'm actually quite confused by what is happening here. So my understanding is that this is a 2-bit field. So Shovik. BSEX. Okay, well, I'm just going to make a bookmark of this. Let's look up what the BSEX register. Oh, this is some other random thing, I guess. This is some. Oh, BSEX must be some other. It's RCTL BSEX, which must be some other bit here that I'm not seeing. Yes, okay, here. Buffer size extension. So we're not using this. So basically what this is saying is the value to put in here depends on the value you put in there. So we're not using buffer size extensions. We're also defaulting to 2048, so we actually don't need anything here, which is amazing. VLAN filter, canonical form, discard positive, I don't know. Strip, we do need this one, strip SECRC. SECRC, which is at offset 26. SERX at SECRC. Long packets are disabled by default. Buff size is set to 2048 by default also. I'm just going to kill the palm tree because I need to go soon. So it might be the case that the only thing we need to do here are just those two configurations, because the other state that we wanted to set, which was kind of listed over here, don't allow drum frames and strip the CRC. So we're setting this, but this one is there by default. And we did this already. And so I haven't compiled in a while. Do we still compile? We do compile. What happens now? So I think I did, I didn't do some of these things, but so long pack, right? So I think I am maybe even ready to test this. Set up the queue, blah, blah, blah. Don't, no interrupts, strip stuff. Set the address. You can do a basic test of functionality. Okay. I don't know what will happen, but let's do make run net test input and so I think I actually need to go into my QEMU fork because I don't know if I enabled all of the okay. Here's my QEMU, not my QEMU fork, but like my QEMU clone. Shit, where did I do this? QEMU upstream. How did I do this? It's e1000.c. Okay, so what did I do? I enabled RX error, but not RX. I think I need to go and recompile. I want RX, I want general, I want anything else look good? I don't know. RX error, yeah. So I need to go into QEMU, rebuild. Oh, why is it? Shit. Oh, I need to do Ninja. Shit. Dang. Why is it doing so much stuff? Man, I had a perfectly good build of QEMU. And why is it not working? That is so unfortunate. glib. Ah, okay. That is unfortunate. How to build QEMU. Jesus. How to build QEMU on Mac. Someone save me. Configure. Alright, y'all, I don't know if this is configure. Just configure and make, and root dir should be all you need. Does it have a makefile? Does it have a Ninja? Yeah, I don't know what happened there. It's recompiling my whole QEMU, which I was using that earlier. I mean, Okay, so maybe that just built. I don't know. Let's try a run. And I don't actually need these environment variables because my QEMU is hard-coded. Fuck. Why? Unsigned. I don't know what happened. Can I copy this just into this thing? Segmentation fall, holy shit. Why? Something has gone horribly wrong. Okay, I'm gonna delete my build directory, configure. All right, John was saying that you just need make. Is that true? Maybe make -J? Did that go faster? Did it restart from the beginning? No, okay. Well, we're gonna sit here. I do need to leave kind of soon, but I really would love to see this at least run. What happened to my QEMU hole? It's like seg faulting all of a sudden. Jeez. In the meantime, let's take a look at what's next, or let's just read this. So it says, when you run this, it will transmit an ARP announcement, which using our packet transmission, which QEMU will automatically reply to. Even though your driver can't receive this reply yet, you should see a E1000 unicast match, blah, 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 indicating that a packet was received. If you don't see this, it got filtered out. Make sure you got the boy already right and didn't forget the address valid bit. Okay, so hopefully that works. I feel like this is compiling a little bit slowly. Like I feel like it's not. Where's the old activity monitor? CPP tools. I mean, it is definitely not using all cores. It definitely looks like it's not using all cores. Huh. CPP tools. Should I stop it? I'm gonna stop it. Build. Ninja. Shit. Ninja. Look at how much faster that's going. I mean, I don't know if it's like if it's cached or something, but. Yeah. So, do I have a QEMU system? I don't. Kimu build unsigned. Okay, I don't know. I don't think this is even worth running with anything but the special Kimu because we need the error logging. All right, I think, yeah, sorry, I don't think I can figure this out right now, and I think we'll need to do this next time. Because I gotta go. But yeah, I'm gonna sign off. Thanks a lot for joining. And we will see how this works next week. But yeah, all right, y'all. Have a great week. I'll be here next time. I'll just quickly plug myself. I have a Discord. Feel free to join it if you want to stay in touch. Like, comment, and subscribe. And yeah, have a great week. I'll see you next week. See ya. Bye.